Hello and welcome back to Calculus 2. This is chapter 11 on power series. And when I say power series, I mean power series. This stuff is so powerful and so awesome. I hope you guys will really like it. And we're going to answer some questions that you don't even know you have, but they will be answered. So let's see all of that stuff. So what is a power series? Power series is a infinite series. Let's say it starts at 1, goes to infinity, where you have some coefficient times x to the n. See, we are introducing a variable x inside a series. So if you want to think about these things, you can say sequences are equivalent to numbers, and they are. It's just a list of numbers. And then you have a series, which was the rest of the chapter 10, which was adding those numbers. So you can think of as operations. And now you're going to stick a variable inside and make it into a function. So it's like a higher creature. So you have sequences on the bottom, which are just like numbers. Then you have series on top of that, which is addition of all those numbers. You can think of algebra and computation. And then now we are going to sneak in an x inside and make it into a function, because that x could take on any number. Just like when you have x plus 2, x could be any number. Now you have this x in here, which could be any number. Now this expands into, let's start at 0. Start at 0. So we can have a C0 plus C1x plus C2x squared plus C3x cubed plus ... going on to infinity. These are infinite series, and the reason why they're called power series is because power n, right, is on x. Guys, what do you have on the right hand side? What is that thing? What is that? What is this? Sequence has commas. Sequence is the list. This is a series, but what is this? The form of this equation. Come on, look at this. What is it? Okay, quadratic. What quadratic belongs to? Polynomials. You have an infinite polynomial. Infinite polynomial. Wow. Why is this so cool? Well, we are going to figure out the way to transform any given function into a polynomial. And what's a joke to integrate or differentiate? A polynomial. So this technically crushes everything you ever learned, because there's no need for anything else, right? If you can turn any given function into a polynomial, then why bother learning anything in integration or derivatives or anything like that, because we can just do this all the time, right? Well, there are some caveats here and there, but essentially, yeah, way to waste 2 years of your life. Right? Just remember, power series, and let's see why. Now, these guys can be centered at a value a, and we'll understand later what that means. So if power series is centered at x equals a, then we have the power series 0 to infinity Cn x to the n give us C0 plus C1 x minus a plus C2 x minus a squared plus C3 x minus a cubed plus dot dot dot. So we are introducing this x minus a business, which is going to shift the sequence left or right depending on the value a. If you are centering at -2, then it will have x plus 2, x plus 2, x plus 2 everywhere, and that shifts it to the left to -2. So we'll see what that means when we get there. Right now, we are concerned with this. So what are these things good for? Well, number one, we immediately recognize that on the right-hand side, you have a polynomial. Now, if this is so that we can actually turn any function into a polynomial, it's a big deal. And it's exactly that. So we can take a sine function and write it as the infinite polynomial. You can take e to the 3x and write it as an infinite polynomial. And then you can take e to the 3x times sine and write those as two infinite polynomials and multiply them together and completely skip those evil problems when you have to do integration by parts twice, because you will be just integrating a polynomial instead of those functions. So this has a huge potential. It can approximate functions, approximate values. It can turn stuff that you can't integrate into something that you integrate because you're integrating a polynomial. Now, these are all approximations because, remember, infinite polynomial should have infinitely many terms. You're not going to write infinitely many terms ever. So you have to chop it off somewhere. When we usually chop it off after 4 or 5 terms, because the precision that we get out of 4 or 5 terms is insanely good. Now, before I go into these calculations, how to get this, I want to make sure that you understand first what the hell is going on. So I'm going to give you a graphical approach. We're going to use Desmos now to graph a whole bunch of these functions and see what is happening here. You don't know why. That will be explained in about 20 minutes, 15 minutes. I want to tell you that e to the x is given as 1 plus x squared over 2 plus x cubed over 6 plus x to the 4 over 24 plus x to the 5 over 25 plus dot 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 going forever. Now, before you scream, why? Hold on. Let me just put this down because I want to do some graphs. So please write this in your notes so that you can look at this, because I will switch the screen to do some graphing in Desmos. Okay. So as you are looking at this, I'm going to first graph 1 plus x, which is x plus 1, right? 1 plus x. That's going to be the first one that I graph, along with e to the x is already graphed, as you can see. So 1 plus x. And you see that the blue line, which is 1 plus x, and the red line, which is e to the x, only touch at one point, and the blue line is absolutely terrible approximation for the red line, right? They're just completely divergent from each other, right? But now in the next line, I'm going to add additional term. So that's 1 plus x, which is the old stuff. And now I'm going to add plus x squared divided by 2. X squared divided by 2. Now, what do you see on the graph? You see that the green line bent, and it kind of follows red line for a little bit, right? They're matched for a little bit, and then they go apart again. But I hope that you would agree that you would rather use green line to approximate the red one than blue, right? Because they're kind of close. Now, if you take a look over here on the bottom, for about that much, they kind of match on the y value, right? What do you think is going to happen when I add another term? The new line, whatever color it comes up to be, is going to follow the red line longer. The more terms I put, the more new line is going to bend and match the red line. And it's going to follow it. So here is the next one. I'm going to take what I had before, and I'm going to add plus x cubed divided by 6. Look at that dark blue line. You see that the green one bails from red one right there. This one bails right there, right? It follows the red one longer. See, this is where they start diverging. I can already see the red pixels right there. The green pixels of divergence I can see right there already. So now it's longer for their match than before. Note that the blue line only touched one point, the light blue line, right? Now look at this purple line, bent nicely around. I'm going to add another term because I can. Copy. This is going to be the black line, and I'm going to add plus x to the 4th divided by 24. Oh, guys, I have the wrong number. Yeah, all right, that's fine. Look at the black line. The black line is better than the purple line. It's better than all other lines, and it lies on the red line as much as possible, right? It is still going to diverge. I mean, look at this. It's -4. Red line is here, and the blue line is there. It's terrible, right? But look at this part. That's a damn good match, right? The more terms I add, the longer this polynomial line is going to be matched on top of the red line, which is exponential function. Which is why we can transform the function from e to the x into this polynomial. And now you wonder, what is the precision that you want? How many terms do you get to keep? And usually it's about 4, because you get to be in the neighborhood of the point that you are interested in. Now in this case it was 0 because I don't have x minus, let's say 2, x minus 2 squared, x minus 2 cubed, and so on. I just have x, so that's x minus 0, so we are centered at 0. That means that for some time, to the left of 0 and to the right of 0, they're going to be a very good match. And the further away you are from 0, they're going to start diverging from one another, and you are going to start getting terrible answers. But computing the value in the red line or the black line at, let's say, 0.5, you are going to get virtually the same number. Not going to get the same, but virtually the same. I just noticed a mistake in my... So I fixed it. You'll fix it soon. How many of you took physics already? Did you run into a problem when your professor said, oh, instead of computing this for harmonic motion, well, instead of computing in a sine, just replace sine with x for small angles? Did you challenge that? No. Because your physics professor probably knows what they talk about, right? Well, it's the same idea. Your physics professor replaced sine x with x for small angles. What does that mean? Well, let's ask Mr. Desmos over here. What does that mean? How about, Mr. Desmos, you give us sine of x? Thank you. And how about you just give us x? Look, don't they match for small angles? What is a small angle? Small angle is what? How about pi over 6? How much is pi over 6 if you want to use 1, 2, 3, 4, 5? Is that pi like 3.14? So 3.14 divided by 6, I'm just going to call that a half because I'm lazy. Where is my half? My half is right here. And my negative half. Don't those two lines look on top of each other? Between the negative pi over 6 and positive pi over 6? They do, right? For small angles, 1 degree, 6 degrees, 10 degrees, 15 degrees, pi over 6 is 30 degrees. So roughly, between negative 30 and positive 30 degrees, you can replace sine x, a non-linear function, with just x. Oh, come on, the derivative, the integral, for just x. We can do these things, right? Now, where does it come from? This, oh, you can replace it. It comes from power series. The power series for sine starts with the first term being x, and then minus, the next term is going to be x cubed divided by 6, and then plus x to the 5 divided by 120, and so on. So let's go and discover, now that we've seen how these functions work together, the more terms you add, the more precision you get, and the more bends and it stays together for longer. We have seen those graphs. Now let's go and figure out the way to compute these things. So these are called Taylor series. If it's centered at 0, it's called Maclaurin series. Taylor is just a general case. You can center it anyway, so at any value. Maclaurin is just centered at 0. What you see up there is e to the x, which is centered at 0. So that's technically a Maclaurin series, but we can call it Taylor series centered at 0. It's okay. How do I get this? Well, the power series is defined as Cn x to the n. And this Cn is going to be the nth derivative computed at value a divided by n factorial. This is your formula to calculate power series coefficients. So let's calculate that series up there with what we know. My function f of x is e to the x. So now all of its derivatives are also e to the x. So I'm going to calculate 4 derivatives for this one. And the reason why I calculate 4 is it's at 4th derivative where notation changes for these tick marks to a number inside parentheses, which is why you have this type of notation that shows derivative order. So it's in parentheses right there. So you are used to prime and double prime, and sometimes when, we want to be annoying, we put the 3rd derivative, but you haven't seen the 4th derivative or the 5th derivative, because why? Well, now you can go to whatever derivative you want to, because the amount of derivatives you take will give you the next term and the next term and the next term in the power series approximation. So I just need to make sure that you guys know that the notation changes at the 4th derivative. So the 5th will have a 5 in parentheses and 6 in parentheses and so on. Imagine the 10th derivative with tick marks. I mean, come on, right? So we have all of these. It is time for us to put the power series for e to the x, which is given by power series Cn x to the n, which is given by C0 plus C1x plus C2x squared plus C3x cubed plus C4x to the 4. I want to add that term because I already have the 4th derivative, and so on. So looking at the formula up there, my C0 is going to be the 0th derivative computed at a divided by 0 factorial. Well, that's just f of a divided by 1. C1 is the 1st derivative computed at a divided by 1 factorial. Well, that's just f prime a is 0 divided by 1, so it's just f prime of 0. C2 is the 2nd derivative computed at a divided by 2 factorial. In our case, 2nd derivative computed at 0 divided by 2. And so on. So we just need to plug all of these in. E to the x is given as C0 is just 1 times x to the 0, which is also 1, so the whole term is 1. Plus C1. Well, C1 is f prime of 0 times x plus f double prime at 0 divided by 2 factorial times x squared plus f triple prime computed at 0 divided by 3 factorial x cubed plus the 4th derivative computed at 0 divided by 4 factorial times x to the 4th. Yeah, I know, squished, but we got it. So e to the x is equal to 1 plus, this is e to the 0 times x, plus e to the 0 over 2 times x squared, plus e to the 0 over 6 times x cubed, plus e to the 0 over 24 times x to the 4, plus dot 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 going to infinity. E to the 0 is 1, so e to the x is given by 1 plus x squared over 2 plus x cubed over 6 plus x to the 4 over 24 plus dot 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 going on forever. What I did is I converted exponential function into a polynomial function and then I can decide which amount of terms I want to keep. Now, I'm going to write this in blood. Since the power series is centered at x equals 0, which is that A, we can use the polynomial to approximate values of e to the x close to x equals 0. So what is e to the 1/2 equal to? Well, if you use x equals 1/2 on the left, then you better use x equals 1/2 on the right. But you have a polynomial. You can calculate that with a stick in the sand, right? You have 1 plus 1/2 plus 1/2 squared divided by 2 plus 1/2 cubed divided by 6 plus 1/2 to the 4th divided by 24 plus ... This is how you compute things when you're on a desert island and the cell phone battery is dead. You didn't pack your TI-83 because you didn't think you're going to need it, right? And e to 1/2 comes up because you are building something on that island. You can compute to any precision you want by keep adding extra terms, right? Just make sure that you are far enough from the water so the waves don't wash out your calculations before you're done. But stick in the sand gets you calculation of e to 1/2, e raised to 0.5. That's a square root of e, right? Yeah, we're calculating square root of e. Right? Right. So, square root of e is approximated by, and I'm just going to use the first 4 terms because I'm lazy, right? So what do I have? I have 1 plus 1/2 plus 1/4 times 1/2 plus 1/8 times 1/6. And then I'm not going to do this. I'm just going to chop it off, which is why I'm using a squiggly line. Oh, I have the plus equals, so this one is not squiggle. This is a equal because I say it goes to infinity. When it goes to infinity is equal. If you chop it off somewhere, then once you chop it off, it's going to be approximation. So now square root of e is approximated at this. This is 3/2 plus 1/8 plus 1/48. The common denominator is 48. That's going to be 24 times 3, 52, right? 24 times 3? No, not 50, because this is 60 plus 12, 72. Plus 6 plus 1. That's 8, 9, 79/48. Let's see how well we did with this approximation. So if I go in the calculator, 79 divided by 48 is going to give us about 1.6458. And the square root of e on the other side is going to be approximated by 1.6487. We got the sense correctly by computing a half in a polynomial rather than computing the actual. This stuff is powerful. I can approximate sine of 17 degrees like this, as long as I know the power series for sine. If you don't know the power series for sine, well, then that's an issue. So let's find the Taylor series for sine. Centered at x equals 0. So my function f of x is sine x. And I'm going to take 5 derivatives. So derivative of sine x is cosine x. The second derivative is negative sine x. The third derivative is negative cosine x. The fourth derivative, this is where it changes notation, is again sine x. It cycles. The fifth derivative is going to be cosine x, and it will go, if you want to take 10 derivatives, it will keep cycling right through. Great. We know that our power series Cn x to the n, that starts at 0, goes to infinity, is going to be C0 plus C1x plus C2x squared plus C3x cubed plus C4x to the 4 plus C5x to the 5. I took 5 derivatives. So let me go to all the way to C5 over there. The order of the derivative matches these. 0th order of the derivative is the original function. Right? 0th derivative means no derivative, so it's original function. That's what you have. Okay. I am computing this at a equals 0, which means that all of my f to the n's will be computed at 0. Now look, every time when you have a sine, that 0 will give you 0. But when you have a cosine, cosine of 0 is 1. So technically, every single one of these that has a sine is going to eventually die out. But let's write it all. Sine x is equal to C0. Well, that's sine of 0. Plus C1. Let me write this. The Cn is equal to Fn computed at 0 divided by n factorial. Right? That's what we are using to come up with these. So C1 is the first derivative, which is now cosine. So that's cosine of 0 divided by 1 factorial. Well, that's 1 times x. Then we have a minus, because it's a minus sign, so minus sine of 0 divided by 2 factorial x squared. The next one is also minus cosine of 0 divided by 3 factorial x cubed. The next one is plus a sign for the fourth one. So plus sine of 0 divided by 4 factorial x to the 4th. And finally plus cosine of 0 divided by 5 factorial with x to the 5. Every sine 0 goes to 0, killing those terms. By the way, it's plus dot dot dot. So sine x is equal to cosine of 0 is 1, divided by 1 is 1, so the first term is x. Remember how they say you can replace your sine with x? There it is. Right? That's the first term, one term approximation, which is why you can't really go far for small angles. The next term is dead. Now I have the cubed term, and that's going to be minus x cubed over 6, because 3 factorial is 1 times 2 times 3, that's a 6. The fourth term with the 4 factorial over there is dead because of sine 0. Then I have plus, and now I have cosine of 0 is 1. I have x to the 5 over 120. Now I hope that you can see the pattern, because not pictured in this procedure here, the next term must be x to the 7 divided by 7 factorial plus x to the 9 divided by 9 factorial minus x to 11 divided by 11 factorial plus going on forever. Do we all see the pattern? What is the interesting thing that you see in terms of the polynomial? What pattern does it emerge? What are you observing easily, guys? Come on. It's right there on the surface. What is the pattern? What? Increasing by 2? Odd. Do we all see odd exponents? 1, 3, 5, 7, 9, 11? What did you learn in pre-calc? This is one of those questions that you have and you don't know you have that as a question. What did you learn about sine function in the pre-calculus course? It's odd function, right? Did you ever ask your professor why? Well, good thing, because the only thing your professor would probably say is, oh, you have to wait for Calc 2 to see why. There's your power series expansion, the Taylor series for sine. It has all odd exponents. What do you think is going to happen with cosine? It's going to have all even ones. So you're going to have x squared, and then x to the 4, and 6, and 8, and 10. And they're going to be all even. And that's why sine and cosine are odd function or even function. Look at our polynomial expansions. So now we are going to cut away again to Desmos and add more terms to what we already started before. You see my x there, right? That was the blue one. What's my next one? It's going to be x minus x cubed divided by 6. So do we all agree that this dark purple is tracing the blue line better than the straight green line? Yes, it is. What's going to happen as I add another term? It's going to bend on it on the light blue function even better. Can I change that to red by clicking over here? No. Oh, tough luck. I can only turn it on and off. Okay, x to the 4. I have, no. I have this plus x to the 5 divided by 120. Look at the black line. You see how the black line almost bends exactly on the blue line, which is the sine function? It bends all the way from negative pi to pi over 2 to pi over 2. If we are using 3 terms, we can pretty much calculate the values of sine from negative pi over 2 to positive pi over 2, 2 quadrants worth of calculations by replacing them in x's. You have to do that in radians. You can't do 17 degrees. You have to convert that into radians, decimal, and then plug it in there and get the value. Do we all see that they match all the way to negative pi over 2, all the way to positive pi over 2? The light blue is the original sine function, and the black function here is my 3-term approximation. I'm going to kick in with one more, and then you will see that pretty much is going to match the entire sine function here. So when I copy this, put it there, minus x to the 7 divided by 7 factorial, I get the red line, which pretty much snakes through the entire sine function that is displayed currently on the. Now, is the red function it? No. No, because it is going to diverge. It's a polynomial, right? So we see that eventually your sine is going to continue there and the red line right goes down. But the red one is the best approximation because you see the black one was the previous one and it bailed right here. The red one bails right there. So every new term is going to bend your function more and more to match the original function. We did that with e to the x. Now you're seeing it, the same behavior with sine to the x. So what Taylor series do, they take whatever function you have, and through the procedure that we've seen with derivatives and plugging these things in, they change that function into a polynomial. And where we're going with this is, so we can say tomorrow, we can say, well, instead of differentiating, integrating, or going crazy with any of these functions, let's just change them all to polynomials and then just play with polynomials rather than working with e to the x, sine x, and anything else. Because polynomials are easy to integrate, easy to differentiate. They have their problems, right? What's easy for exponential and trigonometric functions? To find zeros. What's one of the scariest things in mathematics? To find zeros of polynomial. Yeah, we have quadratic equation for squared polynomial, right? What are you going to do for the 4th degree? There's no, well, there is a procedure that takes about 2 hours to come up with the 1 out of 4 roots. And then good luck with the rest of them. And if you don't know that, just look up the procedure for the quadratic equation. You take a look for the equivalent of the quadratic formula for the 3-root one. Woo. Cubic. Let's see if I can find the formulas for cubic written out. Usually people, oh, there's one. This is the formula to calculate 1 out of 3. X equals this plus b minus 3a. This is a formula to compute because you will have ax cubed plus bx squared plus cx plus d, right? That's the cubic one. And if you want to find zeros of that, this is what you do instead of the quadratic formula for the 3rd power. And it should take about 10 minutes to compute all 3 of them because you have 3 formulas like this. I mean, they're listed in these, you can find them, right? The 4th degree I did once. It took me 2 hours to grind through the whole procedure to find for the 4th degree, like x to the 4th. I got it wrong, and I never did it again, because why? We have approximation for that. There is a proof in mathematics that says that the procedure or the formula do not exist for the 5th degree and on. So we have easy to find on the linear, right? Just x-intercept. You use quadratic formula to calculate zeros for the x squared. You use that monstrosity for the first one out of 3 roots for the cubic one. The 4th one is that insane procedure that takes forever. And then for 5 and on, right? So polynomials are not a joke if you need roots, but they're a joke to differentiate and integrate and do all of these other things. So we would like to have a procedure, which is what Taylor polynomials are. We would like to have a procedure that turns these functions into polynomials so that we can do calculus easy, right? And if you need zeros and stuff like that, well, then keep it in e to the x and sine and so on, because they're easy to deal with, at least for that much. We will finish this tomorrow, chapter 11. I have more stuff to talk about in Taylor polynomials, so I'm not done with this lecture yet. We'll do more of this stuff and finish up chapter 11 tomorrow. So be here. Ciao.